In this video, I want to talk a little bit about the running over different attribute classes inside Wrangle node. So at the end of this video, we get the same result and running. So basically, we have 4 different Wrangle nodes, and we run, and each one of them are run over detail, vertices, points, and primitives. But we get basically the same result. So how can we approach kind of getting the same result, since maybe not always you can use over the class that you are most comfortable with. So should be pretty fun, and we also talk a little bit about the tangent, so let's get to it. For the setup, it's very simple. We have a couple of curves, we resample them, and then we put down a wrangle. Now let's try to get the same tangent attribute running over the details, primitive, points, and vertices. So first of all, I'm going to open up in my external editor. And there's actually a very nice add-on for the Visual Studio Code, and I'm sure for any other of these editors, you can actually get the vex expressions inside your Visual Studio Code. So go ahead to the extensions and just search for vex. It's going to be the first one. It's basically going to enable all of the vex functions inside our Visual Studio Code. It's very nice, it's pretty amazing if you're working with vex. You basically get all of the functions. You see, I'm starting right point. You can see all of the functions. It starts with a point. You can enter it, and you can see it's very easily. You can read what each space is actually needed to be entered. So it's very nice. So if you're working with this, it's definitely way to go get this add-on. So let's just start, and also you get the automatic update inside Houdini also with this. So this is really the way to go. So let's get started. For the actual result that we are looking for, let's put down it's called orientation along the curve node. Let's feed our resampled curve, and you can see that if you start visualize the normal attribute, which is the tangent for this curve by default, and let's for the tangent type, let's put down to the next edge. You will see that every vector is basically a vector that's going to point to the next point. So from this point, it's going to point to the next point. The vector will point, so that's, and every one of these is basically following the next point. So this is just for the visualization, what we are actually looking for to do with every one of these wrangles that we're going to do over the primitives, point, vertices, and details. So how can we do this inside wrangle? Let's start by running over the points. So we have a couple of problems right now, because since the points there cannot be a duplicate points, we have to be very wary of what points we are referencing for every one point that we want to subtract from. So especially at the end, so let's put in the point number. So let's say, so we are at the very end of the first curve, and let's say we want to now get the tangent for the 43. Obviously for the next point, if you run over the points, it's going to go in a sequence, so it's going to start looking at for 44 if we subtract just by taking one vector to the next. So it's going to take this one, and our tangent is going to be not correct. So what we have to do is basically make sure that once it reaches the end of the primitive one, it's going to take not this, but we are basically going to subtract from the previous vector, and then we're going to basically invert the vector outwards for the last point of each primitive. Let's get last point for each one of our primitives. So for that, what I'm going to do is actually create a array. So I'm going to call it prim points. Make sure you have square brackets to identify it's an array. I'm going to use the prim points function. So prim points, just put into, and for the primitive number, add prim num. So even though we are running over the point, or we are running over the points, it still knows which primitive is actually we are running over. So basically for all of these points, so how many points we have here? So we have for the first 139 times, the add prim is going to be 0, and after that it's going to show as a 1, 2, and 3 as a primitive number. So that's how we know that array for all of these times it runs over the points is actually going to be the same. And obviously, since it's an array, it's going to be in sequence. We can actually get the last point by by pointing at it with a -1. So now just as an integer, let's call it a last point. Last point is going to be our primitive prim point, and in square brackets identify the index of it. So since you want to go backwards, you basically want to get the last point of that one, of that primitive point is going to be -1. So now when we run over, we know the last point of it. So basically, once we reach it, now when we reach the last point of this, and we compare it to the last point of our array, we know that we can do something a little bit different than we did with all of the rest of them. Now that we have our last point, let's get the position of our point that we are running currently over. So let's point the vector. I'm going to call it position1. And so we could use a point function, which is basically point, and attribute name is going to be p, and point number is going to be at pt now, which is the current point we are running over. So, but if you want to get the attribute of what we're running over, so of any of these point attributes, there's actually a little bit of a shortcut for it. So what you can do is actually v at, this is the vector, since its position is a vector, v at op input, and then we have to specify the input that we want to get the attribute from. So we're using the first one. So since it starts from 0, it's op input 0 underscore, and then the attributes name. So it's a position. So just a p, and that's it. So instead of using a point function, we just use the op input. We get the position of the current point that we are running over. Now that we have our current point position that we are running over, now I want to make sure that we select the correct next point. With that, it's going to do with if-else statement. So, but we could start with if and write in multiple lines, but we actually can do it in a kind of like a one line. So first of all, make sure that it's going to be a vector, and I'm going to call it position2 equals, and then what I'll do is make a condition which value are we going to select when. So we're going to make sure that when the at pt num, when the current point we are running over is equal with the last point, then the question mark. So this is the way you can do it in one line, kind of. We want to make sure that the position that we take is, then we just use the point as 0, attribute name is going to be position, and the point number is going to be the current point subtracted by 1. So basically a previous point that we are running over right now. So this is when the last point is, actually we are running over the last point. But if it is not, we just want to take, select the next point. So just copy this one. So basically you put in colon, and then basically the condition is going to be if this is not true. So which is going to be the most of the time. Instead of subtract, we just want to add one, and that's it. So this is going to select the right position every time. Now that we have our two positions, let's create some tangents. So I'm just going to create a vector, call it tangent, and just subtract position 1 from position 2. And that's it. And let's create a variable v at, I call it tangent equals our variable tangent, and that's it. So let's start visualizing these. So go to here and press on this one and make sure that it's a tangent, and let's go to the visualizer. See, it's now it doesn't show anything. Just go to the tangent and make sure that it's a marker, and it's a vector trail like that. And you can even change the scale of it, but this is just for the visualization. We could probably want to do a little bit of our own setup. So you can see it looks for the most part fine, except for the very end. But you will notice that our variants are basically let's make it, you can see, let's make it something like this. You can see that our very end vector is actually pointing right back to the previous point, every one of these, like that. So what we want to do is basically invert this vector to the way we can invert vectors is just multiply by -1. but we want to multiply it by -1 only these ends of it. So what we want to do is actually create another variable with the same method we did inside here. So let's do this above here. Let's create a float. Let's call it direction equals. So if at ptnum equals last point, what we want to do is multiply the vector by -1. But else we want to just multiply by 1. Because if you multiply vector by 1, it basically does nothing. But if we do it by -1, it's going to reverse it. No, basically reverse it. So and just make sure that in this vector tangent, what we do is once we subtract it, make sure it's like that, and then just multiply it by our direction float, and that's it. So now you will notice that our ends are basically pointing outwards, like they should probably do. And now let's talk a little bit about normalization of the vectors. So let's take a look and go back in here. See, there's an option for us to normalize vectors, which is basically going to make sure that every vector is the same length of it. Because I'm going to demonstrate like this. So instead of, let's say we do not use a position tool like that, and let's just comment it out, and let's say we use our position as just an X point. So this is going to screw up our ends, but it's actually going to show how unnormalized vectors would look like. So just use a point, 0, attribute name is going to be position, and point number is going to be at ptnum plus 1. So we are basically doing the same thing. Let's position 2. So you will notice that since these basically these points, how far these points are, basically since we did our resample, these points are pretty much the same distance between them. Maybe there's a little bit of difference, but basically the same difference. But you can see at our end, our vectors are very long because, well, it subtracts from this and it looks for 24, which is all the way here. That's why our vector is super long. So we probably do not want to do this. So we want to normalize them. And all we have to do is, in a vector, before we write it out, normalize it. Because basically just a function with normalization. You can see now all of our vectors are the same length, and we can even control how long they are. So this is basically going to put our vector to the 1. Its length is going to become 1. So since these are very long, these are pretty long. This is pretty big curves I wrote, so it's almost 10 meters long. But this basically vector is going to be now 1. Every one of these is going to be 1 meter long vector, and we can also multiply them. So once we have normalized them, we can actually multiply them by channel. So I have basically a length of it. So I'm going to reference the CHF length like that. Now we can basically control how long we want our vectors to be, like that. And one thing you will notice that actually since we do not have our setup for our position, you will see that the very last vector. So where is it? You can see that if I go to the negative, it's actually going to start. Basically, this is the very last point, and since it doesn't have a next point to look at, it basically says that it basically looks for the very origin of our grid, which is at 0. You can see that very last vector is actually pointing at the 0 coordinates in our grid. So that's pretty cool to look at. But let's delete this position 2 and let's use our shortened div like that. Let's make our vectors maybe one long like that. So I think that does it for this. You see, it's basically now our normalization doesn't do anything for our visualization. So since it's already normalized. And for visualization we can actually also, but this is for visualization though, so this wouldn't actually go ahead and change any of these actual values. Let's take a look at where is our tangent. You see tangent is actually changing, but in here it's just for visualization purposes. Now let's get the same result running over the primitives. So what I'm going to do is actually make sure this is still a point. I'm going to duplicate it. And what I'm going to do is actually, if you want to keep working on the same and not open a new window for next triangle, just copy it and still work on the original. You see, we can still now delete it. But you can see our previous one is still as a copy, so I'm going to call it point tangent. This is just going to, at the end, we can take a look at it. So now let's do the primitive tangent. If you want to run through the primitives, we have to do a couple of things. So first of all, let's go back to the point and copy this primitive points variable. So we still want to get every point that is inside every primitive. So that's going to be very valuable information for us. Now let's actually get the length of this array. So I'm going to call it point count, basically ln, which is, and then array reference prim points. It's basically going to say still how many points you have for each one of these primitives. And now we have to do some looping. So there's exactly for the, if you want to loop over the arrays, there's for each loop, which is exactly designed for it. So you can see we inside our Visual Studio Code, it's basically automatically going to set up our curly brackets and all of the items that you can put inside the array. So first of all, it's going to be the, so the index is actually optional, but we still, so basically we can only, for each we can get only array and then basically the value of it, or we can also get the index of the array. So, and since we want also the index of the array, let's keep all of this. So first of all, it's going to be index. I'm called index, the item, I'm going to call it pt, and array is prim points, like that. And this now is becoming very similar to our point triangle. So let's go to our point triangle. Actually, let's copy this, how we get our vectors. Let's just copy these and paste them inside our loop. Maybe like that. And let's paste them inside. So what we want to do is do a little bit of modification. So first of all, we want to position one is going to be, let's use a point function. So it's going to be 0. Attribute name is going to be p, and the point number is going to be our array value. So that's going to be a pt. And for our position 2, we have to take a look at it. So first of all, index. So basically we want to make sure that when we are at the last index, we want to subtract. So let's go to the if the index, basically when the index is at the last point. So the index starts at 0, but the point count starts from 1. So we want to make sure that our point count is, we subtract 1 from it. So basically when the index is equal with the point count, which makes sure that we are at the last point of our, for each loop, we are at the last loop. We want to make sure that we pick the previous point, which is pt, and then we subtract 1 from it, and then basically at pt num we replace with pt plus 1, like that. And this is it. This is basically all of it. And let's copy the tangent and then the writing into the attributes. It is a little bit more different. So the tangent is still going to be basically the same. We get in a loop, we get our tangent, and let's write it out. So we can't use it v at tangent because, well, we're running this. We are not actually well, it's not going to put it. So basically, this would be written into the. This would actually write to the. Let's actually delete this direction. This would actually write to the primitive. All it's basically, whenever we are at, it's going to write to the to that to that context that will be primitive. So what we want to do is use some of these cool functions that we can use in Vex. So this is going to be set point attrib, and this is exactly what we want. So geohandler will be 0, the name of it. Let's call it tangent prim. The point number that we want to set this value at is going to be a pt. So the mode is optional, so delete it. So basically this is where we can basically add to it to the existing value or whatever. So we just want to set it, so delete the mode, and the value is going to be a tangent, like that. Close it down, and let's take a look at our tangent. So you can see it's going to create our tangent. So let's uncheck this, make sure that it's a marker, and it's a vector trail, like that. Let's increase it. You can see we are getting the same result. Let's make colors different. But you can see we are basically getting the same tangent. And let's do it also the direction. So let's start with direction inside here. If the direction is the same as, let's copy this, paste inside here. If index negative, and then just multiply by direction, like that. So this should fix the ends of it. So let's take a look at it. So negative, and then the direction equals negative 1. There we go, it's fixed it. And didn't copy the negative 1, so also let's normalize the tangent and write it out. And then also let's also actually we could also do it all of this inside here, so let's actually normalize outside here. So let's just do this, basically do all of this and then normalize it. And then just multiply by the ch float, which is the length, like that. That should be it. Did I wrote it wrong? Oh, no, it's correct. Actually, I was looking at this one. So now basically we are getting the same result as with our point. If you want to calculate tangent for the running over the vertices, well, for the curves, that for this example is actually pretty simple, because for every point there's only one vertex. So let's take a look at it. So let's go to the vertex for our geometry spreadsheet, and at the very bottom you can see there's only 76 of them. So basically this is the same amount as our point amount. And with curves it's always going to be that, because for every point there's only one vertex. So it will be different if we had a box. And for every point, since we have 8 points inside here, and we know that for every one of these points we have 3 vertices. So let's take it to the vertex, you can see, and if you go to the sort them, you can see for every point we actually have 3 vertices. So this would be a little different if you want to do something with the geometry like that, since it would run over 24 times, not the same amount of times as with the points, like in this example. And now let's purpose our point code, which basically I just copied the Wrangle node. I'm going to write this vertex tang, and just make sure it's at you run over the vertices the same code. You can see there is one problem that our vertex it's not completely correct. That's because first of all we get our positions we are getting at the P position, and this is actually, since we are not running over the points, this actually does not work, so we have to use the point function. So well, let's just write it out. Point 0 is going to be P, and you can use either at ptnum like that, or we can use the at vtx now. So this is basically a linear vertex number. So this is the same as inside our vertices. Basically these are the linear vertex numbers. So you see that vertex numbers has its own number based on its primitive it's attached to, and it is the linear value. So at vtx_num is the linear value of it. We can also extrapolate something like 23 of each primitive, but that would be maybe a different video. But it's vtx_num, and at ptnum is basically the same thing inside here, because it's the same amount of points and the vertices for our curves, like that. You can see our code is basically the same one as in here. So let's rename it tangent vertex, my bad, and let's visualize it. So now it is going to be a vertex attribute. Let's turn off these. Let's put down to the vertex. It's going to be a marker. Let's put in some color, maybe like a green one. Let's make it fixed color, something like this. And that's it for this one. It basically should be the same one. Let's turn on all of the markers for this, and this. You can see they're basically the same ones. Same thing happening. And now let's do the last one, which is detail. Let's just copy some of these. Actually, let's actually put down a wrangle, empty wrangle, because I have to still reopen it anyway. So the detail is going to run only one time, so we have to really make sure that we use our loops correctly. First of all, let's start by getting the number of primitives we actually have. So since we have 4, there is actually global kind of a, I guess you would call it an attribute. So it's going to be an int, so I'm going to call it prim amount. Let's call it prim count, I guess, equals at numprim. So this is basically going to give us a amount of primitives. It's going to be 4 in this. It's pretty simple to remember. So numprim and primnum. So numprim is going to give us the amount of prim overall, and primnum is going to give the current primitive we are running over. So, but since we are at the detail, it doesn't really help us for us to primnum. So, and with this, we can actually start running the loop. So this time we're going to use a for loop. So it's going to be, int is going to be 0, and the count is going to be prim count. So basically this is going to run over 4 times, and each time we want to increase by 1. You can see by this add-on, it's very nicely created for us this loop already. So basically this is not going to go to the 4 because e has to be smaller than prim count. Now that we have created a way for us to run it 4 times, we can start actually reusing some of this prim code. So what we're going to do is actually just, let's copy to get the prim points of the every primitive, and instead of the at primnum, we just have to change it to the y, since this is actually the value that is changing for each loop. It's going to take every primitive number for each loop, and then you can actually just take a look at and copy all of this for each loop inside here, and let's just paste inside. Let's tab out everything that is after for each, and let's do some changes. So first of all, for each index, pt, and prim points, this is correct. We are referencing our array, and remember that in our perimeter tangent we actually had the length of the prim point. So let's copy this one, and we want to paste inside before, or actually after the prim points, but not inside the loop. So now we have this is correctly done. So let's take a look at it. So direction, index, point count, this should be fine. The position, the PT. So the only problem is that in this loop I guess we call it PT. Actually in here it's also PT. The Y is the primitive. So this is actually, I think this should actually work already. Everything should work actually. And we set the point attribute. We could also set it as yes as a vertex attribute. And let's actually visualize it. So let's call it detail like that. And let's take a look at it. Let's create our length of it. So tangent detail, and let's go to the marker. Let's turn off all of these to make sure that we actually, so it's going to be that's not the right one. Detail. We want to marker vector trail. So there it is. Let's give us some color. Maybe something like had blue, like red. Let's make it yellow. Yeah, that's good. And that's it. I think we have done it over the details also. Let's call it detail tangent. Let's take a look at all of them. And in the visualizer, turn on all of these tangents. Let's take a look at them. So you can see the only thing that's changed are the color. And what's with this one? Oh, I turned it to the, for some reason, to details. So you can see we are basically getting the same result and running over the every context for it. And that's it for this video. Thank you for watching, and see you next time.